Hello folks, my name is Tim and welcome back to my channel. So in today's video we're going to be taking a look at the analog to digital conversion capabilities of the Raspberry Pi Pico, also known as ADC. So let's get started. Okay, so ADC is not a particularly broad topic, especially if you have a microcontroller like the Pico here that has ADC hardware built in. However, it is a very important topic if you need to interface with analog peripherals. Now, these analog devices work by using continuously varying voltage levels. Digital devices, on the other hand, use a threshold voltage. Basically, any voltage on a digital pin that is lower than the threshold will be considered to have a low logic level, and any voltage over the threshold will be considered high. And if you keep on increasing the voltage after you hit the threshold level, it won't really have any effect on the pin's output value, but it might release the magic smoke and break your microcontroller. So, if we want to use varying voltage level with a digital controller, we're going to need special hardware to convert a voltage into a digital value that we can use. The Raspberry Pi Pico here has 3 such ADC converters built in. ADC 0 is broken out to GPIO pin 26, physical pin 31, and that's just this white wire here. ADC 1 is broken out to GPIO pin 27, physical pin 32, and that's the yellow wire here. The next pin, pin 33, is the ADC ground pin, and that's followed by ADC 2, and that's broken out to physical pin 34 or GPIO pin 28, and that's the blue wire here. And then finally we have pin 35 here, and this is the ADC VREF or voltage reference, basically a known voltage value that will be considered as the maximum value we can get back on any of the ADC input pins. And we'll see how to wire this up in just a moment. For today's project, we will obviously need an analog device to work with, and I've selected this little thumbstick here. And this should be instantly familiar to anyone who's ever used a PlayStation-style game controller. This thing just has a few input pins, one for the input voltage, another for the ground, and 2 output pins that correspond to the X, that's the left and right movement of the joystick, and the Y-axis, that's the up and down movement. It also has a little clicky stick switch built in, but we won't be using that today. Okay, let's get this thing wired up and take a look at the voltages we get back using our multimeter. Right, so we have our voltage and ground pins connected, and I've just broken out the X and Y axis pins to these wires here, so we can connect our meter and get a reading. But the first thing we need to measure is our VREF voltage. Okay, so as expected, that's around 3.3 volts. That's the voltage the Pico likes to operate at. It's a little bit lower, but it's close enough. Now, with the thumbstick in the center position here, let's take a reading from the X-axis. Okay, so that's about, well, 1.5 volts, roughly around half of our VREF. And it makes sense that when the thumbstick is in the center position, about halfway between its minimum and maximum positions, we would get back a value that's halfway between 0 and our VREF maximum. So now let's test the Y-axis. And yes, that's basically the same. There's a little bit of variation, but then these are cheap parts, so that's to be expected. Now watch what happens when I move the thumbstick. As I push it up, the voltage starts to drop down to 0, and then as I pull it back, the voltage climbs up to our 3.3 volt VREF, give or take. So as the thumbstick moves between its maximum and minimum physical extents, the voltage we measure moves between 0 and our maximum. And this means that, of course, by measuring the voltage, we're basically able to measure the position of the thumbstick. Basically, this thumbstick uses something called a voltage divider, and it looks like this. Depending on the values of the resistors R1 and R2, a given quantity between 0 and 100% of the voltage provided at V in will be sent to V out. And as those resistance values change, so does the output voltage percentage. Now, a very simple way to create a varying voltage divider like this is, of course, to use a potentiometer. And taking a look at our thumbstick and seeing how it's built, we can see what looks like a little potentiometer here on the x-axis and another one here on the y-axis. And as we move the thumbstick, those potentiometers can be seen to turn. And thus the output voltage changes accordingly. Okay, enough theory for now. Let's write some software to read back the values of the ADC pins in Micropython. So over on my Raspberry Pi 4 desktop here, I have the Phony IDE open with the code for a very simple program. So first of all, we just import the needed modules here, and then later on we activate our two ADC inputs, one corresponding to the x-axis and one to the y. Here we're just saying ADC interface 0 and ADC interface 1. We have a couple of temporary variables, and these are just used to limit the streaming of outputs just a little bit to make it readable. And then we dive into a little loop here. So we're saying, first of all, val x is equal to adcx.read u16, and the same for val y. So that's where we read the value back from the ADC pin. We do a little sleep here, again, just to slow the program down a bit so we can read the output. And then finally, we just have a little conditional here to say if the value has changed from the last value, then print it out, because we don't really want it to print out a load of values that are all the same. So let's run the program and see what we get. Okay, so there we are. We're streaming some values out. Now this is a 16-bit value that we get back from the Raspberry Pi Pico's ADC hardware, and that gives us 2 to the power of 16 as a maximum value that we can represent. That's 65,535, and you can see here we're getting values back that are roughly halfway in that range. So we're getting 33,000-ish, give or take, coming back for our two axes. Now, if I move the joystick here, there we are, you can see the x-axis has dropped right down there. And if I pull the x-axis back up, back to the center position, you can see we're getting a roughly middle value. And if I pull the joystick back, there we are, that goes all the way up to 65,000-ish. So there we are, we can see what the x-axis is doing by reading back these values. And for the y-axis, there we are, we've gone up to 65,000. I've just pulled it across all the way to the right. And if I push it to the left, there we are, we can see the value has dropped. So there we are, that's the software side of this. There isn't very much to it, and obviously you can use those values you get back to control whatever peripheral you're interested in. Okay, that's very useful, but before we move on, we need to talk a little about precision. On this graph, I've plotted a theoretical voltage level against physical position that we might see coming back from our thumbstick. You can see it's a nice linear graph, smoothly moving from 0 volts up to our maximum and passing through every value in between. Now, if I add the corresponding digital values to the graph, oh dear, that looks very different. And this is because of precision. A digital number can only represent so many unique values. In the case of the Pico's 16-bit ADC, we have around 65,000 values or so. But if we were using an 8-bit ADC, this would only be 256 values. In both cases, the analog input is of course the same. It basically has perfect precision, passing through every possible value between its minimum and maximum. Since we can't represent this perfect precision with a digital value, we have to sample the input and do our best to encode what we see using the precision that is available to us. This means that many input values will map to the same output value, and you can see this in the graph if we zoom in a little. Within one digital step, that's one output value, we have many analog input values. Now, since we can't tell those values apart, we basically lose that data. For this little thumbstick, I doubt I could move it precisely enough to need 256 values per axis, let alone the 65,000 values that the Pico gives us. But for some applications like audio recording, this is a very, very important subject, and a lot of time and effort is invested in making very precise ADCs and their counterparts, DACs or DACs, that's a digital to analog converters, because the quality of these circuits makes a massive difference to the fidelity of the resulting audio. Anyway, now that we understand ADC, let's use it to do something a bit more interesting than just printing numbers. I'm going to connect these two SG90 servos to our Pico and control their position using a PWM signal that is itself controlled by the ADC values we get back for our X and Y thumbstick positions. Since I made a video previously on how to drive these servos, I won't go over it again now, but I'll embed a link in case you want to go and check that out. And of course, all the code will be uploaded to my GitHub repo as normal. Okay, so that's got everything wired up. I've just added a 5-volt supply here, and that's to power the two SG90 servos. So these guys are just connected back to that supply, and the PWM signal is connected to GPIO pin 0 and GPIO pin 1 on the Raspberry Pi Pico here. Now, the duty cycle of those two PWM signals, that's controlled by the X and Y axis of our little thumbstick here. So let's run the software and see if this works. Okay, so first I'll try the X axis. Oh, there we go. Well, that's working. All right, now I'll try the Y axis. Okay, there we go. So these servos now move around depending on the value of the X and Y axis of this little thumbstick. So we're basically using ADC to sample the voltage back, convert that to a digital value, and then use that digital value to control the pulse width modulation signal duty cycle that operates these servos. Oh, that's very nice. Okay, so I hope that was interesting, and thank you for watching.